Hey folks, welcome. Dr. Emily here. And today we have a really important topic to talk about today, and that is Big O. What is it and why do we need it? And if you're here, drop a message in the chat so I can say hello. And I want to make sure that we're really getting your questions answered today. So please pop them in the comments so I can, really help you move forward. Our goal today is to talk specifically about one tiny area of computer science known as Big O. Where does this help you? Why are we even talking about this at all? And it's because Big O often comes into play in something called the technical interview. It's the gatekeeper for some of these tech jobs that are out there. And with Big O, it's not something you can learn overnight. And you often don't hear about it unless you're in programming specifically or computer science. It's part of a bigger area of computer science called data structures and algorithms, which is typically where the technical interview focuses. Now, I'm also going to hint at when Big O is actually used in the day-to-day life of a programmer. It is. Big O does come into play, just not nearly to the level they emphasize it typically in a technical interview. All right. So let's dive into this. Okay. So as we get started today, I do want to just call out your attention to one key thing is why you're here, the dream, right? Having that remote lifestyle and diving in to what you want to create as a coder and being able to have that amazing lifestyle, that quality of life that you're looking for. And so something just happened, right? Something just happened called AI. I don't know if you've been hanging out here for a minute, right? Vibe coding, Copilot. There's so many different options there. And so this is something that everyone is facing right now. So what's happening to our dream, and the elephant in the room is AI with all these other coding things that are out there. So I just want to take a minute before we dive into Big O to talk about what this means for getting a coding job in the age of AI. Because ultimately, you wouldn't be watching this video if you didn't want to understand how Big O is used in helping you have an amazingly lucrative career in tech. So the question becomes, is AI the answer? Are all the tech jobs gone because AI exists? Well, it's true. AI is disrupting the industry, right? Everywhere, AI is disrupting things. And so it's not just in tech. AI is robbing people of jobs in many areas. But here's the thing is AI is just eliminating the mediocre. It's raising the bar. Let me explain a little bit. So there's a lot of AI code generation tools that are out there. Okay? Here's the kicker. It doesn't mean you don't need coders, right? Just full stop. You still need coders. Oh my goodness. It's really great for prototypes. In fact, I talk with people who have coding skills that are entrepreneurs that actually want to create coding products, right? And they use these tools to help them build a prototype, right? So it's reducing the cost of innovation drastically. It's also making the coding capabilities of existing coders who are senior level way faster. They all have like this army of coders at their disposal, just these AI coding bots, right? But here's the thing. What if you actually want to create something that works? Okay, here's the issue and why AI is not stealing anyone's job anytime soon. Because there is still a technical need attached to the AI. Someone has to actually prompt it what to do and then actually get it working live, online, with security, with robustness, with scalability, right? Like when you want it to work. Let me give you an example. So literally just last week, I was like, all right, I have an idea for an app. Let me just see. Like I could go have a team build it for me, whatever. Let me just see what I can do on my own. Let me push this. All right. So I go through and I'm sitting here clicking, click, and it's cool. It generates this beautiful app, just a couple pages. It looks awesome. And then I get over here. It's a really simple app, by the way. It's like you shake it and it gives you, it's like heads up, but you shake it anyways. It's like super simple. It's like a 2-screen app. Okay, I do this app and there's an error. NPM install. So for anyone that has coded any length of time, NPM install is your first step. It makes sure you can actually run the app. And Bolt has this beautiful capability that it can deploy once it's created. I was like, cool, let me see this. I want to get this up and running with the push of a button. This sounds awesome. Okay, command failed. Okay, but attempt to fix. Cool. Let me see what it can do. Click, 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 click. Okay, an hour later, this is the same problem. It cannot deploy. Okay. And this isn't just an isolated incident. I was talking with another person who is trying to start, has a startup idea, and they did the same thing. And they had it working perfectly. And then the version changed, and now it's not. So the idea is that these skills that you're learning, taking the time to master Big O, are so critically important, because at the end of the day, these prototyping tools are great. They will take you far, but they are not going to build a sustainable business. I'm not, there's no investors who are going to invest in this. Like I can't take this to someone and get investment capital. The person I was speaking with, they need someone with the hands-on skills and technical tools to be able to actually get this up and running, to build a business around it. You're not building a business around these AI-based prototypes, right? You still have to have a person who can go in and tweak things and figure things out, right? Because otherwise you're going to get a lot of code that's super complex that you can't do anything with. I think that's where people miss the boat, is that, spinning something up from scratch is like, that's the easy part. That's like 20%. Like if you want a business, like a SaaS business that actually generates revenue, 80% is editing the code that's already there. And if you use 100% AI without experienced oversight, you are going to have a hot freaking mess. Okay. And it's going to become so expensive to maintain, it could surpass the company's ability to generate revenue. Okay. What I just say, I'm going to dial this in, because again, I'm talking to like a coding audience. I wear two hats: entrepreneur for startups and also coding educator. And so the idea is that if you're not cautious and careful with how you create the code, you are going to end up with a tangled, hot mess of code that no one can fix, not even AI, and becomes so expensive to maintain, the company will literally go out of business. So these jobs, what you're learning, keep going. That's the short of it. Keep going, because your skills are needed. The rub is at entry level, the bar has been raised. And so you need to know more to be useful and to get employed. Not that the jobs aren't there. It's just they've changed, right? You actually need to know more than AI, basically, right? Is where things are going. Awesome sauce, folks. So super, super awesome. So just drawing your attention to the fact that, when things don't work, there's where that human comes in. And wouldn't it be awesome if they knew how to debug? Fortunately, that's exactly what we teach inside TechJoy in the TechJoy Career Academy. So if you're interested in knowing more about the future of coding in the age of AI, please join us next Thursday at 9 p.m. Eastern. I'm having my next masterclass. In fact, I'll drop it in the comments for you. All right. There we go. That should link to it. So please feel free to join us live. And we're also going to be talking about how you can skip entry level and jump into upper level tech positions. All right. So super awesome. So hope I can see some of you guys there. All right. Super, super cool. Awesome. So let's dive in to what the real focus of today, which is Big O. All right. Let's focus on Big O. What the heck is this thing? Right now, remember, Big O, the purpose of this is on the technical interview, you're going to be asked about this, right? There's Big O, login, Big O of n squared, Big O of 1. By the end of our video today, you're going to understand all of those things, okay? And if you're not certain about anything, please don't hesitate to pop it in the chat. I love to answer your questions. So what the heck is Big O? So Big O is a tool that computer scientists use to compare two different solutions to the same problem, okay? Let me give you an example. All right. How do I sort a list of numbers? I know this is a super boring example. It's based in math, but that's where computer science was born. So we're going to use the typical example. How do I sort a list of numbers? So let's say I have two solutions. I have solution A and I have solution B. Awesome. But to be honest, comparing them is kind of like comparing apples and oranges. So which one is going to be faster in general? Which one's going to be faster just for my data? Right? They're each different algorithms, different approaches to solving the same thing, to sorting a list of numbers. But gosh, like, how do I compare them? And it's not just about my data, but in general, right? So computer scientists want to know which one is going to be faster all the time, no matter what. But then there can also be variations. So let's say you have a list of mostly sorted numbers. Oh, well, maybe solution A is better at mostly sorted when you just have one or two out of place. Maybe solution B is better when it's totally reverse order sorted. Like it's like totally messed up and there's nothing in order. Maybe solution B performs better. And so sometimes there's variations in how these solutions work that optimize them for different types of problems. And so Big O gives us, it's a tool that we can use to compare these different approaches. Okay, these different approaches. Awesome sauce, folks. And I hope you'll ask questions in the comments. Let me know if you have any. So let's dive in just a little bit more. So Big O, at the end of the day, is going to help us measure efficiency in terms of time and space, right? So you're going to have two pieces of code that do the same thing. Fancy pants word is their functionally equivalent. And how do you compare them? Which one takes more time? Which one takes up more space, right? Which one takes up more memory? And so these are the two variables that we have to play with. And how are we going to measure it? Okay, there's a couple different ways to measure it, and I'll show you today. But the way a computer scientist measures it, like someone who's focused on theory, not with reality. So there's some relationships here. It has impact in reality, but I'm going to show you today there are limits to how this tool, this Big O tool, can be used. The way we measure Big O is by counting the number of algorithmic steps. This is a fancy pants word for saying how many things does it do? How many operations? How many additions? How many subtractions? How many loops? How many ifs and else's, right? And if you wanted to, you could put the theory to the test in practice by doing what's called profiling, which is when you measure how long a piece of code takes to run on a particular data set. So you can even figure out in practice which approach is faster, which to be honest is usually what most companies do. But Big O gives us a broader tool that allows us to compare no matter what the underlying technology is. Okay, super awesome. Awesome. So Eric's got a question. Do some coding disciplines call these Big N, or is that something else? Eric, I think I'm going to answer that question before the end of today. But typically what you hear is Big O of N, right? So N is usually the data size, right? And N is just a variable. It's like a free floating thing. It could be any number from 1 to infinity. So Big O of N, I'll explain what that is in just a second. There also are two other forms of Big O that I'll get into at the very, very end. We don't normally see them, but I want you guys to have this knowledge, okay? We're not locking this away in the ivory tower, okay? So great questions. Keep them coming. So in terms of efficiency, time and space. So computers are fast. They got lots of memory. So why do we even care about how fast something is, how efficient something is, right? But sometimes space matters. So if you're building an app for a phone, it can matter very deeply how much space or memory a solution is taking up. For instance, most of the apps that you see on your phone are not doing the heavy lifting. The heavy lifting is happening on the server on the other side of the internet. And in some cases, the server might only send your phone, like if you're searching something, it might send you like 6 results. And that's it until you hit next. And then it loads the next. Because if it actually sat there and sorted and loaded everything, it would take so long, you would just like give up in frustration, be like, oh, this never works, right? So, paying attention to this actually really has direct impacts to the user experience, to how the app performs, how it looks and feels, okay? So we do sometimes want to care about efficiency. And everything I'm telling you about today is not this or that, it's when. When do you want to care about this? What is your particular situation? And these are the questions as a software developer that you need to be asking, right? So that you can get it right. This is how you keep your job, right? And you get hired again because you do an awesome job because you actually understand the requirements. This is why there's a lot more to building software than just grunting out the code, right? And this is why humans are still ahead of the AI, all right? So computers are fast and have lots of memory, so we do need to care about efficiency for certain contexts, certain places, okay? And then also, if you're doing large data computations, so this is of concern to places like, like scientific labs, NASA, NIH, places that are number crunching huge data sets, right? Especially, I mean, I saw this all the time in NASA, Oak Ridge National Laboratories, places like that. They're going to be number crunching huge volumes of data. And all of a sudden it makes a difference, right? Like if it takes a minute to sort 100 numbers, okay, like you might sit there for a minute and wait as a human. But what if you were going to do billions of numbers, like modeling something on the moon, right? Like, okay, now you really need like a minute. Oh, no, this isn't going to end in your lifetime, right? Okay, now we need to pay attention. And so this is where some of these approaches have come, is because like hardware changes, like the computer, the technology, it changes over time. It gets faster. But in this moment, you might actually want a result before tomorrow, right? Or before next month. In fact, when I was a PhD student, we used to run experiments that took 3 months to run. Oh, and it was really frustrating when we'd find a bug a month in, right? But you can actually run computations that take too long, that literally take forever. And so sometimes we have to be careful of these things and be intentional. Okay, so today I'm giving you the tools so that you can be smarter about how you're coding. Okay, super awesome, super, super awesome. And there's also trade-offs between time and space. Okay, so time is how long the program takes to run with a given data set. Space is how much memory it takes up to perform that task. So if you want, you can really limit space if you're allowing a longer time. Let me give you an example. Let's say I'm squaring or I'm multiplying every number in a list by 2, right? And there might be some repeats in that list. If there's repeats, I could use something like a dictionary to store that data and look it up later, like a lookup table. That would take up more space and would have faster time. Or if I don't have that kind of space, let's say I have a really long list, I would just compute that multiplication by 2 for every number in that list. It's going to take more time, but I'm not going to take up any more space than necessary. Okay, so these are always trade-offs. These are tools that we have in our toolbox. All right, super awesome. Yep, and so we can go faster when we have space because we can do lookups, we can cache or store the information for later, and we go slower if there's less space, more computation. Okay. So let me give you guys an example. I know this is a pretty boring math example, but it's very simple to understand. And so it helps here. The example is to sum or add the numbers from 1 up to some n. I don't know what n is. That's the whole point of Big O, is that I don't have to know what n is. And I can still compare solution A and solution B. I can compare 2 solutions of apples and oranges, even when I don't know how big the data is. So what are some possible solutions? Okay, I'm going to share these with you folks. If you're a mathematician, you might already know some of these answers. I'm going to share 3 different solutions to this problem. So the one on the left is A. That's just a simple loop that sums them all together. This is typical if you just started programming and you're in the beginning phases, you'd probably come up with solution A. Solution B, no one in their right mind is going to do, but we're using it for the purposes of example here. So we've got a loop from 1 to n and a loop from 1 to I, and we're adding 1 repeatedly. So solution algorithm B is adding the number 1 a gazillion times. Solution A is just summing all the numbers together. And then algorithm C is the fancy pants mathematics version, where there's actually an equation that will tell you what the sum of the numbers from 1 to n is. So someone who's brand new to this problem, who's never looked at it before, their brute force approach, it's going to be A, right? Algorithm A, just create a loop, sum the numbers from 1 to n using a variable, right? Super simple. But someone who's done a little bit more research might know that there is actually a formula that they can use to actually get this number, okay? So think to yourself which one you think is going to be fastest, no matter what the n is, no matter how many numbers we want to sum together, which one is going to be best, okay? Let's take a look. Okay. So to compare algorithms A, B, and C, we are going to count what's called the algorithmic steps. This is a tool that we're using to help us understand Big O, okay? So the algorithmic steps are the basic operations of the algorithm that have the biggest impact on the time that it's going to take. And to be honest, most other operations are going to be ignored, except for loops. And if you understand this concept, recursion. Recursion is just a function that calls itself. I have another video on that one if you want, and loops as well. So we're going to count the number of calculations here because this problem is a math problem. So basically the operations are all arithmetic: addition, subtraction, division, things like that. So for algorithm A, we had a loop and we're adding one number at each repetition of the loop. So it's going to have n additions. Algorithm B is the one that no one in their right mind would ever code up naturally, but we're going to use it for the purpose of example. We're adding 1 a gazillion times. Okay, we're adding 1 a gazillion times. And so that one, the number of like additions is actually n squared plus n divided by 2. Oh my goodness, it's a quadratic freaking formula. All right, like this is a very complicated one. Algorithm C, however, was the formula where we literally just calculated what the sum would be based on some arithmetic. And that only has 3 operations. Whoa, okay. So in terms of basic operations, these vary a little bit. Okay, let's dive into this a little bit more. Let's dive into this. All right. Okay, so I don't know if you guys remember plotting graphs back in math class, right? So let's say we really push this n as far as we can go. You do not have to know calculus or advanced math to be a programmer, but so big O is about as mathy as it gets. If you have experience with calculus, you may recognize the idea of a limit. Big O is basically the limit if we push the data size n as big as it can get. Okay, if you've never heard of calculus or limits, then ignore what I just said. Don't let it confuse you. All right. So the idea, though, is if you plot the numbers on an XY graph, right, how fast does that formula increase? How fast does that equation grow? So what does this mean? If I increase the number of data, the size of n by a little bit, how much does my time change, right? That's what we're looking at here in this basic graph. So we can see that algorithm A was pretty simple. It's adding the numbers, right, from 1 to n. So as n increases, the time increases. And you see this nice straight line, okay? I don't know if you guys can see my pointing here, but algorithm A has this nice straight line. Algorithm C is the holy grail here. Doesn't matter how big n gets, it's the same time. That is what you want to see all the time in the code that you write. Algorithm B, freaking pain, n squared plus n over 2, it's growing fast. It's a quadratic formula. Oh my goodness. No, we don't want those. We don't want those. Yeah, this is as mathy as it gets. Oh, you can see it. Oh, perfect. So good. Yep, very mathy. Yes, and I just want to stress, like, this is the one math lesson in months of training that we do inside the Tectoy Career Academy. Like, this is it. This is the mathiest lesson there is. So if you're good with this, you're golden, right? Math is not typically used in the day-to-day life of a full stack or mobile software developer. It is used for theoretical computer scientists who have PhDs. It is used in computer graphics. It is used in machine learning and AI for people that are actually training the models and pushing the boundaries of what AI can do. Okay, cool. So let's take a minute and just look at this big O here. All right, let's look at this big O. So now I'm hoping you're with me so far for at least counting these basic operations and how they grow as the size of the data changes. Now I'm introducing Big O. What the heck is that? And remember, Big O is just a tool. It's a new way to communicate about how quickly these different solutions grow when you change the size of the data. So the purpose of Big O is to compare and contrast different solutions to solving the same problem. Here we have 3 different solutions, A, B, and C. And so what I want you to notice is we've written out the number of operations in terms of n. That size of the data. Are we working with 20 numbers? Are we working with 100 numbers? N stands in for that. It's a variable. So here we've got n squared. So the big O becomes O of n squared. Notice there's no n divided by 2. Like, that stuff all disappears. And this is the cool thing about Big O and why you can use it as a tool, even if you're not super mathy and you've never taken calculus before, because the other pieces actually fall away. So I can communicate with you guys today. I'll be teaching you a very simple way to identify the Big O of something, even if you don't have the advanced fancy pants math, okay? So algorithm A, right, that was just summing the numbers from 1 to n using a simple for loop and a variable. It has n operations. It's going to add n numbers together, O of n. Simple, right? And then the only one that's a little bit different here is algorithm C. This was our constant time algorithm because it was a formula. And it had the same number of operations, no matter how many numbers it was adding together, same number of operations. So that is Big O of 1, constant time. So this one's a little bit transformed, right? There's no n here. Whenever there's no n, it goes to 1, constant time, okay? So that's like kind of back of the napkin. How do you calculate Big O for these different numbers of operations? Okay. And so Eric's asking, so it signifies how much work it uses to solve in some sense, right? It's the number of operations. So it's really an approximation of how many processor, like CPU operations are going to need to be performed to complete this solution. So it takes it away from, I don't care if you're on a Mac or a Windows machine. I don't care if you have 8 cores or 1 core. It doesn't matter. This is the number of operations. So no matter what, no matter which computer you run this on, right? If you have more operations, it's going to take longer to run. That's the idea. Okay. Great question. Great question. Sweet. Okay. Awesome. So let's look at this a little bit more. Okay, folks. And let's actually, are you guys ready to try this out? Do you want to give this a shot? Open? All right. Let me know. Let me know. All right. Sweet. All right. So I want to give you guys a chance to kind of dive into this and do it for yourself. Okay. So let's take some really, really simple loops. Okay. If you've never coded before, it's okay, right? You should still be able to take a stab at this because being able to read and predict code is actually a super key skill. And you don't have to know ahead of time because the skill we're learning is how to read and predict. And it's okay to be wrong, right? So right now I'm going to show you pseudocode loosely based on Python. It's not strictly Python, but it's really to get the ideas across. Okay. Awesome. And so let me just answer these follow-up questions here. Eric's asking, operations aren't all equal in the amount of work. No, right? So that's something we have to be careful of. But at the end of the day, the operations should be basic, like arithmetic. If an operation is like a function call, you would actually need to go into that function and count the operations, right? So typically the operations should be around the same amount of work. So like adding, subtracting, dividing, multiplying, all those basic arithmetic operations, squaring, like checking to see if something is 0, like comparisons, they're all approximately the same amount of time. So that's the level of depth of operation that we're looking for. You're not going to have operations that take like if it's a function call, you're going to break that down. Let's say that function call is 100 operations. You're going to add that in, right? So you're really getting it down to like the lowest level. All right. Great question. Awesome sauce. All right. So let's take a look at a couple. All right. So I've got a loop here for I in 1 to 10, print I. Again, this is pseudocode. It's kind of like Python. What it's saying is we're going to print out the numbers from 1 to 10. Okay. And then I have another loop for I in range 2 to 21 to 2. It's going to output the even numbers 2 through 20. Okay. Both of these solutions are outputting 10 numbers, but they're doing it differently. Okay. So if I want to count the number of basic operations, they're both printing. So I'm going to take that as my operation of 1. Okay. But I think, Eric, what you were saying about not all the operations being the same amount of work is one of the limitations of this tool of Big O versus just running it in practice. Okay. And we're going to talk about that before the end. Okay. So we've got 2 different solutions here. Can anyone take a guess how many steps are here? How many steps are actually happening? How many steps would you guys count for the left one and the right one? Doesn't matter. And you can just pop in the chat. What do you guys think? Just curious. What do people think? this could be. We'll see. We'll see how many prints. Let's start with that. Let's make the basic operation print. How many prints? How many numbers are getting printed in these examples? Can anyone pop it in the chat for me so I can see it? I'm hoping I can get something in the chat. Nobody's willing to say. Everybody's shy. All right. So if I'm printing out the numbers from 1 to 10, I'm printing out 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. I'm printing out 10 things. So the loop on the left over here is doing 10 operations. Let's go to the right loop. I'm right. Yes. Eric got it typed in. Woohoo. There's probably a lag. That was probably a lag. Super awesome. So then on the right, we're doing for I in range 2, 21, 2. So I am simplifying this. I'm ignoring the range function call, right? And I'm focusing on the fact that I'm printing out the numbers 2 through 20, all even. So 2, 4, 6, 8, 10, 12, 14, 16, 18, 20. That's 10 too, okay? So both of these are actually outputting, they're outputting 10 numbers. They're taking 10 algorithmic steps, okay? Does anyone have a guess as to what the big O might be? So if you're thinking about it, jot it down and I'll tell you in a few minutes, okay? Write it down. Okay, let's try this one. For I in range 10. So the loop is gonna go 10 times. If the number is even, print it out. Okay, print it out. So this is gonna output just 5 numbers. 2, 4, 6, 8, 10. Okay, 5 numbers. It's gonna output the even numbers from 1 to 10. But yes, yeah, Sam's got it. Yep, it's still 10 algorithmic steps, right? In fact, it might even be a little bit more because it's doing a second thing for each one. So we're looping 10 times and then we have an if and then we're printing. So this one actually takes more than the one in the top left. It's printing out less numbers, but it's actually calculating. It's calculating more. It's doing more work to get fewer numbers to the screen. So that's why you can't just use the printing. It is the collective of all the operations going into it. Awesome job, folks. Awesome job. So all of these have 10. Now there's no N here, right? All of these are just printing out. So for the way I have structured these, right? All are O of 1 constant time. They're printing out 10 numbers, right? They're all taking 10 steps. But if we were to say that these are all N, then they would be O of N, right? Because for I in 1 to N, it's going to do this once for every number 1 to N. So it's still going to be O of N. Okay, great. Awesome sauce, folks. So let's look at this. Let's go a little bit deeper. All right. So we practice harder than we play the game. Let's go into this a little bit. This is the basics. Okay, this is the basics. And there's more. There's more. So let's talk about that. So we've talked a little bit so far about O of 1 versus O of N. Okay. So like O of 1 is constant time. It doesn't matter how big N is, O of 1 happens. In this case, I don't have any N's defined on the screen, but let's say 10 or 21 was actually an N. All of these would be O of N. All of these would be O of N. Okay, excellent. So if we get in the habit of looking, which algorithm is faster? Okay, which algorithm is faster? I know I'm going back to the graphs because they're really the fastest way to see this information. O of N is just cut straight in the middle. For every number of elements, for every way I increase N, the number of steps is going up. The time, it's going up, right up the middle. Okay, that's like, okay, that's not exactly what we want to be seeing. What do we want to be seeing? Things like O of 1, that formula, those algorithm C to sort numbers before, or count the numbers 1 to N before. And then there's this other one, O of log N. What the heck is this? So O of log N has an N in it, but it's a lot closer to O of 1. It's not O of N. How do we get over here? Like, what does O log N look like? And so this is one of the holy grails of computer science is how do you take something that's O of N and make it O of log N? Or how do you take something that's O of N squared and make it O of log N? So let me just unpack for a hot second what log N looks like, okay? So what is O of log n? O of log n happens whenever you split your problem in half repeatedly, right? So let's say you've got a set of 16 numbers, and then you analyze 8 and 8, and then you analyze 4, 4, and 4, and 4, and then 2, 2, 2, right? Like whenever you're splitting your problem in half every time, you're getting log n. A simple way to think of this is, I'm looking for an example here. A simple way to think about this is if you have an old-fashioned telephone book. Has anyone here used a telephone book? Or if you have a dictionary and you're looking for, so if you have a phone book and you're looking for a number, or you have a dictionary, you're looking for a word, you might take that book and open it in half, and then you'd open it in half again, and you'd figure out, oh, do I need to go left or right? How am I going to get to that right page number that I'm looking for? Or even if you're looking for a page number, right? If you're splitting your problem in half, you've got a problem that could be a contender for log n, Okay, awesome. And Anthony actually did use phone books, which is awesome. Right, another number game, higher or lower. Exactly, folks. So O of log n is just you're splitting the thing in half, right? So now if you want to calculate it, technically log of n is a base 2 log, because computers are binary, zeros and ones. So 2 to the n is 8. You could use the log function to figure out what n is. So that's what, if you remember log from math class. If you don't, it's okay. Like, this is only used for web development if you're analyzing the big O, right? So this is literally the only place you need to use it. And it's basically you're repeatedly dividing. And how many times you can divide is what the log is. And so with these operations being log n, you can see that if I have 128 elements and I've got an O of n solution, it's going to take 128 operations. But if I have a log n solution, it's going to take just 7, right? So that's going to grow way closer to constant time than O of n, which is going to go right across the way. So let me just show that visually for you guys. So this has more colors and more functions on it. So the green line is O of n. And then what you can see is O of n squared is the red one. And there's more beyond it. They grow so fast, they're like off the screen. We want to be over here, right? So the purple is O of 1. Look at O of log n. It's so close, it might as well be O of 1. It's close enough. The way we do that for other, like there might be an n squared algorithm, O of n log n, the orange, right? We want to get it close to O of n. And so these are really the holy grails in computer science when you're solving a problem, is that you really want to find solutions that are O of log n or O of n log n. You want to avoid O of n unless you're willing to take it, unless it's a reasonable solution for your particular application. Okay. Awesome sauce. So I love this graphic, right? This is, kind of like a heat map of where we want to be when we're creating our programs. And where does this come into play in practice is don't nest your loops, like period, full stop. If you have to have a loop, have it only repeat once instead of 3 times, right? Basically, these are the tricks. But if you're someone who's really pushing the boundaries of what technology can do for our society, these actually matter, because you might be coming up with brand new approaches to solve problems. So like O log n, O of 1, this is the green happy place, good and excellent. Even O of n, it's not the best, but okay, if it's what you got, it's what you got. O of n log n is really good. It helps us cut down the O of n squared problems. Things over here, O of n squared, O of 2 to the n, O of n factorial. Oh my gosh, these are like awful. When would you see these? O of n squared is a nested loop where you loop from 1 to n. 1 to n, 1 to n. When you nest loops, you multiply the big O together. That's how you get those big N squareds. O to 2 to the n, any kind of two-way communication problem. Let's say you've got 5 friends standing in a circle and you need to pass a note between each one. That's going to be O2 of n type problem. O of n factorial, I'll be honest, I don't recall seeing it personally, because most of us avoid that like the plague. But factorials are multiplying. So you would say, let's say factorial of 5 would be 5 times 4 times 3 times 2. So that would be like a nested loop, would have to have that. And it's looping for n. like, right, like, and going down from there. Recursive examples sometimes are factorials as well. So it can get to be a real hot mess. And this is why, like, if you're working on something like sorting or searching, we often will just, as programmers, we're just going to use the off the shelf solution. The libraries that are out there have typically been researched for like decades to make them as efficient and quick as possible. Like in terms of sorting and searching, there's like, dozens and dozens of really fast algorithms that people have spent decades implementing, tweaking, and developing. And so typically we're not going to be coming up with these on our own. We're just going to use the libraries that are out there. But sometimes you find yourself in a position where you do actually need to create something new that's never been done before. But more often than not, the way this comes into play is being intentional with how you're actually constructing your code, right? How you put your loops together matters. Are you nesting your loops? Are you doing one right after the other? Do you have like 3 loops doing this, like one operation each over the same data set, the same end? Can you put them together? That's going to save your program time. So it's really the way we really use Big O typically in a day-to-day programmer's life. I think Sam was asking for this as well. The way we typically use it is just and being thoughtful in how we create the programs that we're writing, right? Like, are we doing unnecessary operations? If you've been following us for any length of time, one of the, principles we promote is dryness. Don't repeat yourself. So are you doing anything extra? Are you doing more work than is necessary? And then we can focus from there. The way this comes into play to get your foot in the door, though, is typically it might come up on a technical interview, okay? Because companies want to hire programmers that know how to avoid unnecessary time and complexity in the code that they write. Okay, awesome sauce, folks. So I have just a couple more things I want to touch on to close this out, and then we'll go from there. All right. So there are limits to Big O. In practice, it's usually better for a software developer to just run the darn thing. Now, it could be that implementing different solutions might take time. So you might look at the Big O first to kind of narrow your field so you're not spending all day long implementing things. But usually things where you're comparing Big O are already implemented in general purpose libraries because a lot of other people have needed to do those things too. But just so you know how this varies, the Big O in practice might be different for your particular data set. So one thing you can do is to profile, right? And what that looks like is you would take your program and you would actually run it for a couple different data sets of typical size. So let's say you expect to run it with 100 numbers normally. You would do maybe 4 or 5 different scenarios with at least 100 numbers. Maybe you try 1,000 numbers. But the idea is that you want to run it multiple times because when you're profiling, profiling is when you measure the actual time that it takes. When you're profiling, it's true that, your computer could start running things, right? And other things can happen. It's not going to be the same every single time. And so you want to do it a couple times so you can get an average so you know approximately how much it happens. So this was an example where someone took some O of N code and ran it and how long it would take, right? So let's say the log of N took microseconds, O of N took 1 second. Then O of N log N might take 20 seconds, but O of N squared might take 11 days. N cubed, so this is if you assume N is 1 second, right? So N cubed is going to take 31,000 years. This is where I'm talking about, like, you actually want to be attentive because you may not get to solve your problem in your lifetime kind of thing, right? And that's just the difference between N squared to N cubed when N is 1 second, right? And then 2 to the N is light years, right? It's huge. So we do want to use both tools in our toolbox. What I typically find is in practice, developers are actually using profiling and how long it takes, right? Like, time to the first, interaction and time to first load, things like that are typically more common in the day-to-day life of a software developer. But to pass the technical interview, you may be asked some of these heavy questions about what is Big O, and you want to arm yourself with this vocabulary so you can talk intelligently about it. Okay. Last thing is someone else had asked about this, about Big N, right? So it's Big O of N, but there are other options. So today we talked about the worst case scenario, big O. Big O is, what if the wrong choice got made every single time, right? What's going to happen in the worst case as we get and bigger? That's because big O is a tool that helps us be conservative, right? Which is going to be the worst. But there's also best case and average case, known as big omega and big theta, respectively. They're not often used. I don't often see them, but just to be complete in terms of, talking about what's out there, I wanted to share them with you today. All right. And so, if you have questions about Big O, how to pass your technical interview, how to get experience, even in the age of AI, right, to get your foot in the door, definitely reach out to us, the TechJoy Career Academy. We can absolutely help support your training and learning and job hunt. And in fact, if you're interested, folks, if you'd like to know more about the future of coding in the age of AI, I'm going to talk about it at my live masterclass next Thursday at 9 p.m. Eastern. And in fact, you can sign up at https://joc.mobi. So let me type that in the chat. Let's see if I can do it again. I didn't think to. There we go. joc.mobi, and you can sign up. And we're also going to be talking about how you can skip entry level and jump straight into upper level tech positions. So I think what we're seeing now is with AI is that entry levels are disappearing. But the problem is that senior dev positions are still there and they're still lucrative. So if you'd like to see an alternative pathway to use your skills to start earning, even as you grow and learn, definitely join me next Thursday at the masterclass. All right, folks. Any other questions that I can answer for you today? If you're watching this as a replay, please don't hesitate to reach out, pop in the comments. I absolutely check them and I can get back to you. But don't be a stranger, right? Let us know if you're interested in joining us inside the TechJoy Career Academy. All right. Awesome sauce, folks. It was great to see you today. Awesome questions. And I look forward to seeing you soon. Peace.